Hello students, it is nice to once again come back to the numerical part of it. It looks to me like this will be the last part of the numerical that we'll be doing. So you can cheer up, you can be very happy that numerical is getting over at the end of the time. But this is also a very crucial and important concept that we are going to learn today. So the topic is equilibrium of rigid bodies. So in the equilibrium of rigid bodies, suppose if you have kind of a scale like this and you have a wedge. So you wanted things to be in equilibrium and you try to adjust here and there and try to keep it like this. So it looks pretty okay. Maybe if you keep a big mass, your mass here, right, and another very big mass here, and try to see whether it is in equilibrium or not. So always you need to see this is going to have a reaction here and this is going to have a thing, or maybe this will have a weight W1, this is going to have a weight W2, and this has a reaction. All these things will be there, okay? So whether it can be balancing together, that's the main part of it. So in equilibrium of rigid bodies, there are two main things. Number one is translational equilibrium. Number two is rotational equilibrium. So I will explain to you what is translational equilibrium and what is rotational equilibrium. Okay, suppose if you have a scale like this and there is a wedge like this and it is hanging over it. Now let us consider what is translational equilibrium. Now every force which has been acting on this one you need to take. As soon as you keep the wedge here, the scale is kept here. This one will have a reaction R1. So this wedge will give a reaction R1. Here also R2. And this scale will have its own weight W1. Okay. Let us imagine you tie something else and put a pan here and keep some weight here, right? And this is going to be W2. Now in translational equilibrium, the amount or the sum of forces acting perpendicularly upwards is equal to the sum of the weights acting perpendicularly downwards. The sum of the forces acting upwards should be equal to forces acting downward. Then it is going to be in equilibrium. Of course, it is right. If it is going to be in stationary condition, the total force going upwards should be equal to the total force acting downwards. So how you can write here R1 plus R2, because these two are upwards, is going to be equal to W1 plus W2. So then only it will be in equilibrium. So hope you are able to understand about translational equilibrium, right? The next one is rotational equilibrium. Look at the rotational equilibrium. What is rotational equilibrium is, whenever this body is there, it should be stable. It should be stable. It should not keep on tipping here and there. It should not keep on oscillating here and there. It should be in straight, correct position. Okay. It looks to be like an rotational equilibrium. When it could be a rotational equilibrium is the clockwise rotation should be equal to anti-clockwise rotation. Now you can ask, sir, what is clockwise rotation, what is anti-clockwise rotation? You need to understand this one quite clearly. First thing is, you have to imagine in any point of this particular body a point where you will make the axis. You have to choose the axis. Maybe you can put an axis here, put an axis here, and then the whole body, it just spins around like that. Or you put an axis in the middle, then it rotates like this. Or you put an axis here. It is better to put an axis wherever the force is acting. You can put somewhere else also, no problem. You can put anywhere. It is up to you. You can choose either these 4 points or some other point also. But you, to an extent, now people will try to put in somewhere else where there is a force is there, and it's quite easy also. let us imagine we are going to put an axis at the center of the place itself. Here there is an axis. Okay. Now if there is an axis is over here, then don't consider any other force, only consider one force which is there. Just put an axis here. Just pull this body along this force. Along this, if only R1 is there, pull R1 only. Which direction it will rotate then? It is already fixed here. You're going to pull it here. When you pull it, it will not go straight up there. It will just start rotating only because it is already fixed here. Which direction it will rotate? It will rotate like this. Am I right? Now, rotate R2 now. Don't consider R1. Don't consider W2. Rotate R2. You just pull it up. Which direction it will go? It will go in this direction. Right? So this direction is called clockwise direction. This is R1 is going to be in clockwise direction. This is going to be in anti-clockwise direction. Now, don't consider R1. Don't consider R2. Now consider only W2. In this one, just let us consider only W2. You pull it here. What will happen? It will go in this direction. It will go in this direction. That's the way this whole scale will just rotate. Now you got an idea here. Look at this one. Which is a clockwise rotation? W2 is clockwise rotation. R1 is clockwise rotation. Which is anti-clockwise rotation? R2 is anti-clockwise rotation. Okay. So, how you will do it? R1, the clockwise rotation, into the distance from the axis of rotation. Okay. For example, if this is A, and this is B, and this is O, and this point is C. So what you will write here in clockwise rotation, R1, clockwise rotation we are going to see R1 into this distance here, AO. And what is another clockwise rotation? Here also this is also clockwise rotation. It is going to be equal to W2, the force, into the distance from here to here, OC. That's equal to anti-clockwise rotation. Only one is there, anti-clockwise rotation. That is R2 into what is the distance here? OB. Done. This is what it is. I hope you are able to understand this one. You need to first of all fix an axis and start pulling that one force, and rest every force you just ignore it as if only one force is there. You pull it. Which rotation it will make? Anti-clockwise, clockwise. You need to first of all find out. So R1 has a clockwise and clockwise rotation, R2 has anti-clockwise rotation, and this one it has this one. Now you can ask, sir, what about W? What rotation this will have? Look, when you are putting the axis on this one itself, this one into 0, there is no distance here. So you need not go for any other rotation for W1. So there is a benefit of it. If you don't want to consider that particular thing, you just put axis on that itself. That's great. Okay. So just a small incident I remember. In a big company, they were trying to look for a next managing director. So they wanted to look for the thing. So there was a search committee. The search committee will search for the new managing director. But there is one guy who was quite dominant, and he doesn't want to, he will really dominate. The whole thing he dominates. And people felt this guy should never become a managing director. He will grind everybody into crazy. So the board of directors, they met and find out what to do. This fellow will definitely become a managing director because he's so much famous, he's so much talkative, he's so much into quite an influential thing also. Then finally a smart thing came. Hey, now the smart move is put this fellow in charge of a search committee itself for a managing director. So he was heading the search committee, and here the search committee has to find out a managing director. So what they did, the entire search committee has to revolve around this axis of rotation. The difficult point, you put as axis of rotation itself. So something like that, that guy who had to just to obey the board of directors and then start searching for another managing director. So definitely he didn't become a managing director. So that means definitely this will not come into their clockwise anti-clockwise rotation. W1 will not be there. Okay, hope you are able to understand. Very important concept. There are two equilibriums. Translational equilibrium, the number of forces, the sum of the forces up is equal to the number of forces down, so it is equal here. Rotational equilibrium, the total clockwise rotation, the number of clockwise rotation is equal to total anti-clockwise rotation. But the important point is, which is point of rotational moment. So considering the moment at O, so we here the point is O. So what is that? It is O is the point here. So it has become, the whole thing here has become, this is valid only because O point is being considered. Now you can say, sir, why can't I have B as a point? And can I do that? Yes, you can have B as a point. Then R2 will never appear here. Which will appear? R1 will appear. W will appear. W2 will appear. No problem. You can go ahead. You pull this one, it will be clockwise, and this pull this one. This will also come this way. This will come this way. This will come this way because it's going to be, you're pulling in this direction, this axis. So it's very simple. It will be really beautiful to see how it works. Okay, depends upon the moment of force on this particular axis. I've taken a lot of time to make you to understand. Now we are going to do the numericals now. Okay, let's start with the numericals. So let us consider question number 42 now. Read the question carefully. A uniform plank AB, 16 meter long, weighs 15 kg W. A plank is there, 16 meter long, supported symmetrically on two posts C and D, 7 meter apart. That means, so one post is like this, another post is like this. I don't know how long the post is, how high the post is, low. This is supported like this, right? So this is one post and this is one post, and this is 16 meter long. Okay, and this is 7 meter, from here to here 7 meter is there. Now a boy, so this is going to be center. Okay, a boy weighing 60 kg starts from C. So here is C and D. So I will put C and D. A boy 60 kg starts from C and moves beyond D. Alright, so he is moving beyond D. So what happens to, okay, it is better to take this as C and D because it just goes like this. Okay, so let us again read this one. A boy of 60 kg starts from C. He is starting from here. He is walking down. He is in the middle and he goes to the D. Okay, very good. Then what happens? This boy goes beyond D. Now what will parents shout? Hey, don't run. Don't go beyond. Now what happens here? When he goes beyond, this entire plank will just tip. It will just go on a slide. You would have seen it is not a small one, it is a 16 meter long big one. So estimate the distance up to which the boy can go beyond D before the plank tips. So what distance this guy can go so that it will be still safe for him before it tips? Quite a interesting question. Alright, so very nice to look at this question. So hope you are able to understand. 16 meter long, this is 7 meter from here to here. Two things are there, and this boy is going beyond, and he is going to, some moment of time, this entire plank is going to just tip up, and he is going to just slide down. So what point he can go, then put a red line there, don't go beyond this, because his weight is also there, 60 kg weight. So first of all, translation equilibrium you can have. What is the translation equilibrium? R1 is here, and then what is he going to say? R2 is here, and then this whole thing also weight is there, W, and this is also another weight is there, W dash. R1 plus R2 is going to be equal to W plus W dash. This is quite a obvious one. Let us go for a translatory equilibrium. Okay, translatory equilibrium already I saw. Translatory equilibrium. What is translational equilibrium? R1 plus R2 is going to be equal to W plus W dash. Right. The next one is rotational equilibrium. Rotational equilibrium. In rotational equilibrium, now you tell me where you need to put the axis. You need to choose the axis. Can you put here, center, or you want to put here? It's up to you. Okay. So let me put here, because R1, R2 we don't know. It's very difficult to find out R1 and R2. So let us put here. Let D be the point of moment of force where the axis of rotation is assumed. You assume the moment axis of rotation at point D. So if it is point D, now tell me what are the ways in which it will be there. So just keep D and then pull R1 force. So it will go like this. It is going to be clockwise rotation. Keep here and don't consider anything else. Pull W. Just it is a rotation here and pull only one force is there, W. It will go like this. It is going to be anti-clockwise direction. And then forget about all the other three. Only here is there. Pull this one down. Now it will come like this. It is going to be also clockwise rotation. So clockwise rotation is 2 are there. This is here. So clockwise rotation is going to be equal to anti-clockwise rotation. So what is the clockwise rotation here? So you need to find out here is R1 into so what is the distance here from here to D? It is already 7 meter is there, because this is going to be 7 meter long, right? 7 meter plus this is also clockwise rotation, W dash into X. We don't know this distance. This is distance is X, is going to be equal to, what is the next one? What is anti-clockwise rotation? W here. Only W is there. So W into, what is the distance here? Distance from here to here. If this is 7 meter and at the center, this is 3.5 into 3.5 meters. Very simple. Force into distance plus force into distance is equal to another force into distance. Clockwise is equal to anti-clockwise. Done. Okay. Now very important thing is, look at this one. If this boy is gone to a point here, when it is just starts tipping, just it is on the verge of leaving, then tell me what is R1 then? It is just on the verge of lifting. So R1 should be equal to 0 at that point of time when it is just lifting. When the boy is at a place when plank just starts tipping, then R1 is going to be equal to 0. So when R1 is going to be equal to 0, so put it here. So here what happens? 0 plus W dash into X is going to be equal to W into 3.5. So what is W dash? This guy's weight is given here. Here, how much is this? 60 kg. So W dash is 60 into G. And what is W? W is the weight of the scale itself, 15 kg weight. W it is 15 G. Put the value here. 60 into G into X is going to be equal to 15 to 3.5. So what's the value here? X is going to be equal to 15 divided by 60 into 3.5 is going to be equal to 3.5 divided by 4. That's going to be equal to X here. So what's the answer you get here? Which will be 0.875 meters. Quite simple. Just a rotational equilibrium only, it is there. And you're able to get this answer. That's all, answer is done. But it's a very interesting question. How far it can go before it tips. But the tricky, important part is we have considered R1 is 0 because it is going to have a reaction which is going to completely nullify. Hope you understood. A good question. Let us go to the next question now. So question number 41 we are going to see. A uniform metal bar, length 70 centimeter and mass 4 kg is placed horizontally on two knife edges pivoted at 10 centimeter from each end. So it is a uniform bar is there like this. So 10 centimeter you have a knife edge and 10 centimeter you have a knife edge. Alright, and this entire thing is 70. This is the center. Okay, so a 6 kg weight is suspended at 30 centimeter from one end, from one of the end 30 centimeter. So somewhere here it will come, because from here center is, this entire is 70, so from here to here is 35, so 5 centimeter you need to have. So something is tied here like this. Okay, so that's 6 kg is weighing here at 30 centimeter from this point. This point is 30 centimeter. Find the reaction of the knife edges. This is reaction R1. This is reaction R2. Find R1 and R2. This is what the question is. Alright. So we will start ahead now. Okay, we'll start going ahead. So you know already what all things to be done. This whole scale or this thing will have its own weight, that is W, and this is going to be W dash and R1 and R2. Okay, so translational equilibrium. R1 plus R2 is going to be equal to W plus W dash. So what is W? W is already given here, 4 kg. W is 4 kg. And what is W dash? W dash is going to be equal to 6 kg. So R1 plus R2 is going to be equal to 4 plus 6 into G, because we need to find out M into G. So it's going to be equal to 10 into 9.8, 98 Newton is R1 plus R2. This is equation number 1. Please remember this. Quite simple. Translational equilibrium will give you R1 plus R2. Now the next thing is we need to see the rotational equilibrium. Now how will you do the rotational equilibrium? What first thing you need to do? Consider the point of axis. Last time we did it for R2. Here we have put the axis. This time you can put anywhere also. Do it anywhere and try to get the answer. For the convenience sake, we can try to do one thing. Put it to the center. Okay. The center is at O. So you can write down. As you consider the axis of rotation, the axis of rotation at O being the moment of okay, so taking moment at that point, moment at that point. moment at that point. Okay, so all the things you need to rotate now. So if this is the one, don't consider W, don't consider W dash, don't consider R2. Now you just pull this one, what will happen? It will rotate here like this, clockwise rotation. And then what happens to R2? Just pull R2, it will rotate like this. And what happens to W dash? Don't consider R1, assume nothing is there, just consider what is W alone, just pull it here. When it is pulled in this axis of rotation, what will happen? This will rotate like this. So W dash and R dash is together the same thing. So what you got to do is, okay, R1, what is the distance of R1? Maybe if this is A and this is B, so it is AO. So this entire thing, please make sure this is there. The entire thing is 70 centimeter. Okay, so this is 10 centimeter already. So what is this one then? 25 centimeter. Alright, this is also 25 centimeter, but this is 30 centimeter. From here it is 35, from here to here it is 35, this is 30. What is this one then? 5 centimeter. Alright, and what is this one then again? 25 centimeter. So all things are quite clear. So R1 into axis of rotation from here to here, what is this one? R1 into 25. R1 25 centimeters there. Let us not make it in meters, just to keep it 25 itself. Plus, what is the next one? These two rotations together. W dash into what is the distance? W dash into what is the distance of axis of rotation? 5 is going to be equal to, this is the opposite one, R2. What is the distance of R2? It is 25. Alright, so you get the thing equal. So moving further down, what you can do is keep R2 here and R1 that side. So R2 minus R1. Take this one next side. Alright. So 25 you can take it common outside. So when you take it out that side and take 25 common outside, R2 minus R1 is going to be equal to W dash into 5. So R2 minus R1 is going to be equal to, what is W dash? 6 kg. 6 kg, 6 into gram, not gram, it is G, 9.8 into 5 by 25. So this is 5. So it is going to be 6 by 5 into 9.8. That is R2 minus R1. So what is the value here? The value you will get is 11.76 newtons you will get if you do this one. That is R2 minus R1. This is equation number 2. Look at equation number 1. R1 plus R2, 9.8. R2 minus R1, 11.6. Can you do the calculation together? R1 plus R2 and R2 minus R1. Try to add both of them together and you will be able to get the value of R1 separately and R2 separately. You will be able to easily get this one because these two are already found out. Please do the calculation. Okay. Now I will go to the next question. So this is a very, very nice, simple, easy question. I think you are now got a hold of it. What is translation equilibrium? What is a rotational equilibrium? So here it is called rotational equilibrium. Here we are going to that rotational equilibrium here. Okay, we'll go to the last question now. Okay. Question number 43. We are going to read the question. As we read, we are going to draw the diagram also. A uniform ladder AB of weight 40 kg is 5 meter long, rests against a smooth vertical wall and a rough horizontal floor. So you find there is a vertical wall is here, right? And in this vertical wall, you are having in the rough surface, a ladder is kept like this. So the height of the wall which the ladder makes in contact is 4 meters from the floor. This is 4 meters and this is 5 meters. So you can consider this is going to have this is the ladder. If this is 5 meter and this is 4 meter, this will be 3 meter because Pythagoras theorem says that. So consider this is A and this is B, right? This is O. Now calculate the reaction at this point and the contact force which its components at the floor. So what is this point? Reaction at this point means the height of the wall at which the makes and the contact is 4 meters from the floor. So this point means contact point at A. Calculate the reaction at this point and the contact force which it's with its components at the floor. So you need to find out the reaction here. Alright. So if you want to put the reaction here, maybe the reaction is somewhere here. We don't know. Maybe it is exactly along this ladder itself. We don't know. Let us consider this R as a reaction. And this R makes an angle theta here. R is making an angle, not this ladder. Okay. So can you make a component like this? What is this component? It is Rx. And the component perpendicular here also, that is Ry. Two components are there. Right? Now, what are the other forces will be acting here? What are the other forces will be acting? Whenever you put here, there will be a force will be acting here. This is Rb. And from A is acting another reaction. This we can call, instead of R, you can call it as Ra. And what is another thing? At the center of mass, you will get a W here. The weight will be there. Okay. So what is Rb? Reaction from wall. What is Ra? Reaction from floor. Okay. So this Ra means what is Rx is going to be equal to Ra cos theta, because this is Ra cos theta, and along horizontal, what is Ry? Ra sin theta along vertical. And what is W? Weight of ladder. Okay, sounds good. It is all now done. Now we need to start having the components. What are the components of the vectors? Okay, translational equilibrium. What is the translational equilibrium? Weight acting down and weight acting upwards. Down and up. So down is W and up is Ry. Okay. And then one more force is also there. Rx is this direction and Rb is this direction. So Rb is going to be equal to Rx. So these are the two things which is we have got it. That is translational equilibrium. We don't have the value here. Let us not put the values, but let us go ahead and see what the next thing is. Right. So this is anyhow it is there. Ry we already know because W is the value 40 kg. So it is going to be equal to 40 into 9.8. We'll get this answer. Rx we don't know. We need to find out. Okay, because this Ry and Rx we found out, then Ra is easy because it is just these two things. Because of these things, you will be able to get the value of Ra. That's what it is find out. So Ra is going to be question mark. That's what the question says. Calculate the reaction at the point of contact. So Ra is question mark. So if you want to find out RA, know Rx and Ry. This Rx and Ry you should know. We don't know Rx now. So we are going to find out using rotational equilibrium. Rotational equilibrium. Now you're all quite experts now. Now you're going to go ahead and do the value where the axis of rotation. Okay, considering the axis where moments are assumed as, which point you can say you want to have A point, or you want to have the middle point, you want to have a B point. Look at this one, A point, if you put, you will be really saving so much things. Every force will become 0, Ry, Ra and Rx, everything will become 0 if you put A as a axis of rotation. If you have here, it's no problem, only W will become 0, but you need to handle all of them. So I would suggest go for A as A. Point A is axis of rotation. So if point A is axis of rotation, what happens here? Just pull this one, keeping point A, pull this one, so it will go like this. Right? It will just rotate like this. Now what happens to here? W, if you put, only W if you pull down, if you pull the force like this, it will come like this. So this is anti-clockwise direction and this is going to be clockwise direction. Only two forces are there. Okay, RB and this one, and here everything is now clouding here itself. So we'll go ahead now and say RB into BO. BO is RB into BO. This is the BO. Okay, is going to be equal to W into this distance. Okay, I can consider this as O dash, AO dash, AO dash. So what is RB? RB into BO. What is BO? BO is going to be equal to 4 meters. W, what is the weight of the ladder? 40. Right? 40 into, this is going to be equal to 1.5 because this is the distance. Here, this is the distance, 1.5 because that is 3. So if that's the way, so what's going to be here? RB is going to be equal to 40 into 1.5 divided by 4, you get 10. RB is going to be equal to 15 into 9.8. Okay. So, or you can consider as 15 into 9.8 also, it's fine, which will become value, or if you want to put 10 also it is okay. I don't mind if you put 10. So it's going to be equal to 150 newtons. That is RB. If RB is this much, 150 newtons, please remember RB is 150 newtons. Now look at this one. We already got the translational equilibrium as RB is going to be equal to Rx. So therefore what is Rx is going to be equal to 150 newtons. Now what is already Ry? W, this is the value. So bringing this one down, so Ry is going to be equal to 40 into 10. So we can take it as 400 newtons because 40 into 9.8 I am taking as 10 itself, 400 newtons. Okay, Ry is there, Rx is there. Now you need to find out R. You need to find out R. So R is going to be equal to under root of Rx square plus Ry square. So it's going to be equal to 150 square plus 400 square under root. You will get R finally. You will get an answer. Theta also you can find out. Tan theta is going to be equal to Ry upon Rx. So it's going to be equal to 400 upon 150. This is tan theta. So it becomes, and here also it is going to be 8 and this is going to be 3 8 by 3 tan theta is equal to 8 by 3 inverse will be there. Alright. Actually the answer is, if you look at the answer, it is 42.7 kg weight is there. In other words, you just put your answer, okay? It will become around 400 something, you will get an answer. Take a look on it, okay? So I will just leave it there. I will not put a value here. It is going to be in newtons, you will get the answer. You will get in newtons. Here also it is going to be 8 by 3, somewhere like this you will get, okay? So good children, it is nice to see all these questions. This is a little different question which has rotational equilibrium like this. It's coming. I think you can definitely do any other question if it comes. I will give you one question in a small as a whole homework. You can do that one, okay? So we will be having a numerical test on next Wednesday. Please start preparing for that. All that I have done till now, that will be asked, okay? So try to prepare for that. Alright children, thank you.